Welcome to the 8th class meeting of the Introduction to DSP. We've just taken our first quiz, which changed it to close everything quiz. I found that large language models such as ChatGPT or Gemini have evolved so quickly, too clever. So the quiz problems we've just taken, when I just gave it to LLMs, the solutions were perfect, more than perfect. So I'm sorry, I changed the format of the quiz. As usual, endless homework will be assigned. So there will be homework 8. And yeah, something's not correct. This should be deleted. Sorry about that. Yeah. And today we are going to study Z transform. It's very simple, but what I have found is that including myself around 30 years ago, even though I learned Z transform in signal gen systems and even in DSP, I had trouble in clarifying some concepts when I became a graduate student and was about to take the graduate level DSP. So I'm trying to clarify all I had suffered. So please focus and see what I say. Here goes the message from me, instructor. In the last class meeting, I emphasized the importance of converting mathematical expressions verbally, such as, for example, convolution in time domain is multiplication in the frequency domain, something like that. So this is very, very actually powerful. When you define something, you just see the mathematical definitions as just the figures. Never do that any longer. Try to verbalize every definition, which enables you to open your toolbox and instantly use what you spend a lot of time to get acquainted with such tools. So try every possible verbalization. Okay, here goes the review of what we had so far. So in order to prepare for the first quiz, I believe you've done this, but anyway, what is most important in digital signal processing, including this one, is to rewrite a discrete time signal or digital signal or vector as a combination of some basis functions from a basis. And this choice of basis depends on applications. So as your graduate or undergraduate study goes on, you will see a lot of new bases. And sometimes such and such basis is very useful for some applications. For another application, another basis is very important. So someday, I hope one of you or more than one of you invent your own basis that is very, very powerful theoretically and also practically, and become a IEEE fellow and in your reception ceremony saying that, hey, this invention of inspired my former professor who taught DSP, then I'll be very happy. Okay, anyway. Fourier basis, by the way, is very sorry about that. Very, very appealing from human color perception because we distinguish the light waves in colors, basically in the frequency domain. Of course, we do not have kind of sensors that spans all the spectrum of the light wave, but we have around 3 cells that somehow non-linearly maps the received signal and try to differentiate different frequencies. Anyway, so the Fourier basis is very, very appealing. However, it was not that, and also in musical instruments, especially string instruments, 현악기. The early days of scientists such as Galileo and even the Isaac Newton could see the vibration of the strings in the musical instruments. And they invented beautiful theories, and that were actually very, very correct. That's why some of your musician friends and you who took signalization systems can converse with about frequency domain, something about musical instruments. Anyway, however, to us, the reason why the Fourier basis is so important is that every discrete time LTI system has the functions from Fourier basis as eigenfunctions. An interesting thing is that when you have a discrete time system, then the eigenvalue corresponding to the that Fourier basis eigenfunction becomes the DT Fourier transform of the impulse response. So it's like this is why the Fourier basis is so important for discrete time LTI systems. So for example, in future someday, you have your own system, and that system with maybe somewhat subset of DT-LTI system or some linear system, then you find some sets of inputs are very, very powerful to reconstruct or to analyze your input signal. And it turns out that each signal is an eigenfunction of the system. Then appearing, just a second. Yeah. Anyway, so yeah, there are very interesting new theories about digital signal processing. Anyway, so here goes the idea of frequency response of a DT-LTI system, which is basically you draw in your brain the DT Fourier transform as function of radian or angular frequency. Then you have low pass filter, band pass filter, high pass filter, sometimes band stop filter, and special band stop filter called notch filter, etc. And also these filters could be ideal filters or non-ideal or practical filters. By the way, as you see here, we will see filter design techniques, and we will see some, where it is, yeah. We will study structures for discrete time systems to better design filters. Anyway, by the way, not only in our previous class meetings, but also including today's class meeting, the linear constant coefficient difference equation plays very important role in the digital signal processing. And I especially emphasize the fact that there are discrete time systems whose input-output relations could be described by an LCCDE. The problem is that the system is not yet guaranteed to be a linear or a linear time invariant because of existence of homogeneous and particular solution or existence of zero input response and zero state response, especially this zero input response makes the system nonlinear. Any linear system must satisfy zero in, zero out. That is the simple consequence of linearity. So existence of nonlinear zero input response makes the system not linear. Fortunately, if the system whose I/O relation described by LCCDE satisfies initial rest, and particularly this is simple for LCCDE because in that case, initial rest condition is the same as a 0 input, 0 output, in that case, you can guarantee that system is LTI. So that system, DT system, falls in to our scope of this course. Okay. So what I'm saying is that the LCCD is very, very important, but you have to be careful because in some cases, the LCCDE is not what you are expecting. So be very, very careful. And also, even if your DT system is described by, DT LTI system is described by LCCDE, be careful because here, LCCDE technique is not that powerful for all, for every case. Sometimes it's very impractical and not that useful. But since we have to design a system using delay components, adders, multipliers, what we do is that we approximate and just saying that, okay, under certain criteria, this approximation is okay. One of my messages from this course is that we electrical engineers have real-world system to be designed and analyzed. And the tool we learn in this course is very mathematical. So we mathematically model the real world, and in every modeling, mathematical modeling, there is some error. That error may be very significant in some cases, sometimes very ignorable. So you have to be very alert in whether your mathematical model is okay or not. That is very, very important. Got it? Anyway, yeah, again, Fibonacci sequence we will see. And also, especially during last few class meetings, we studied the discrete time Fourier transform and its properties. I especially emphasize the difference between the Fourier transform and Fourier Plancherel transform, even though most of the undergraduate textbooks never distinguishes these two transforms, but otherwise it's very confusing because in most of the cases we are interested in the energy of the error signal when we truncate Fourier transform or something, but that is not well reflected by original strict sense definition of DT Fourier transform. Another thing is that the DT Fourier transform does not guarantee that your synthesis, not analysis, but synthesis equation works. But as I emphasized here, one of the reasons why we rely on Fourier transform is that we want to rewrite the signal as a linear combination of weighted sum of Fourier bases. And if that kind of reconstruction does not work, what's the use of analyze the signal? So just a simple original definition of DT Fourier transform does not guarantee something like this. So here you have some signal that is absolutely summable. So you are happy. The problem is, so you have DT Fourier transform. The problem is that from frequency domain, when you want to go back to time domain, this is the procedure you take, right? And in most of your course textbooks, they just say that, hey, these are Fourier transform pairs, so signal can be written this way. It's not correct. Got it? So in order for this to converge, actually, there are some requirements. But simple thing is this one. If we consider square summable sequence, then it is guaranteed that your reconstruction works as far as your equality is in L2 sense, which means that when you approximate right-hand side with summation of many, many terms, then the error has very, very, very small energy. And if you define your resolution, then error goes to 0, something like that. So in practice, this L2 sense is very, very okay. And still, this absolute summability or square summability, you may just ignore. Why? Because in the real world, there is none absolutely summable sequence. There is none square summable sequence because we human race invented the digital signal processing and electrical system. It cannot go back to negative infinity and positive infinity, right? So mathematically speaking, engineering wise speaking, you have to always deal with negative infinity and positive infinity as a good approximation so that your mathematical model can be handled easily. Got it? So don't be too much bothered with some integrability or summability in some cases. Got it? Okay, anyway, properties probably you memorized a lot, so let me skip. So here goes the preview of today's class meeting. As I told you, now we are here about the Z transform. And many of you are already exposed to what is a Z transform, but let me define it one by one. So here goes, not here, where it is. Yeah, here goes the, where is the definition? I forgot. Yeah, okay, let me write down again. So here goes the definition. Okay, given a DT signal, X of n, its Z transform is given by, or defined as, if you want, what? Capital X, we usually use capital X of Z, which is sigma X of n times Z to the negative n, and this time index n is from negative infinity to positive infinity. So some of your bundles of neurons say that, hey, we have infinity, be careful. You are right. Now, let's see some examples. So whenever you see something, let's see some examples. Suppose your discrete time signal is delta of n plus 1/2 delta of n minus 1. Now, what is its Z transform? By the way, as we use the right-left arrow with F to denote the Fourier transform pair, we do the same thing, but F replaced by capital Z or lowercase z to mark that the left-hand side and right-hand side are Z transform pairs. Now, what is it? So let's do it. Sigma n from negative infinity to positive infinity, X of n, Z to the negative n. Then this apparently infinite sum becomes what? Delta of n, Z, sorry. Where is my? So what you do is that you evaluate for all Z. So n less than 0, then xn is 0. So if you visualize X of n, you have here 1, and here 1/2, and all the other time instants you have zeros. So x of 0, z to the negative 0, plus x of 1, z to the negative 1, something like that. And here, this is what? This is 1, and this is 1/2. So you have 1 times z to the 0. So we hesitate a little bit, and 1/2 z to the negative 1. So what do we do about this z to the 0? And as you learned in high school math, whenever we have this base and exponent thing, so 2 to the 3 here, what is this one? This is the base, right? And this is called the exponent. And we read this one, 2 raised to the power of 3 and simply 2 raised to 2 raised 2 to the power of 3, sometimes 2 to the 3, 2 to the 3. For simplicity, right? The full description is that 2 raised to the power of 3. Okay? But people simply say 2 to the power of 3 or 2 to the 3. Okay? So anyway, whenever we have a to the n or something like that, a to the 0 is 1 for a non-zero. And for base 0, we have trouble, right? Yeah. However, in Z transform, actually, we have the definition for n0, we always just remove that one, okay? So our answer is 1 plus 1 over 2 Z to the negative 1. By the way, so far, Z is just a base that can be anything, but actually in the Z transform, Z is a variable, and not just a variable, Z is a complex variable. So Z transform is a function of Z given by something. Got it? So suddenly we have a big trouble. If the base is just used to make the definition look good, but as you see here, and many of your neurons says, we can never divide by 0, right? So we have some trouble writing here. So because Z inverse means 1 over Z, and now Z cannot be 0 in this case. Am I right? So in this case, of course, it's very obvious. If Z can be any complex number, just writing the transform in this way, we exclude Z equals 0, right? But sometimes it's not that clear whether which part is gone in the complex set C or not. We will see soon, okay? Anyway, so Z transform is a transformation method that convert a discrete time signal into a function of Z. Here, Z, this function of Z may have domain in the complex set C. Got it? Now let's see another one. Suppose you have a signal that is this one. What does that mean? So for argument of u less than 0, the value is 0. So this x of n signal is right-sided or causal signal. When n is 0, you have 1. N is, so x minus, x dot 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 up to minus 1 is 0. x0 is 1. x1 is 1/2. x2 is 1/2 squared. And we have infinite non-zero terms, right? Now let me ask you to find the Z transform. And you will suddenly see that your sum, this sum in the definition, is no longer a finite sum. It's an infinite sum, especially countably infinite sum. Following our convention, this part is still 1, but you have 1/2 Z to the negative 1, 1/2 squared, Z to the negative 2, and countably infinite terms. So this is the Z transform, actually. Be careful. Z transform is a function. Z transform of a signal is a function. Whenever you define a function, you not only need mapping rule, but also you need the domain of the function. So what is the domain? So we want to say x is from something to complex number, right? Because you plug in any complex number, you will have a complex number. So what is this domain in this case? Before, for this one, what was the domain? Domain could be complex number minus 0, right? Now, what about this one? So it's very confusing because as you see that, hey, this involves z to the negative 1, so we have to exclude 0. What else? Now, as your high school math teaches you, you know some formula for this kind of geometric sequence or geometric progression. What was that? Initial term, 1 minus common ratio. What is common ratio? Common ratio is this one, right? Now, are we done? So what we usually do is that, okay, if z is not 0, we can multiply z in the numerator and denominator, right? So this becomes z, and that becomes z minus 1/2. Now, if z is not 0, what is not allowed? Z equals 1/2 is not allowed, right? Because that makes this numerator something strange. What else? We also know that the common ratio whose absolute value must be less than 1, right? So this common ratio whose absolute value must be less than 1. And if z is non-zero, then we have 1/2 and z, if I remember correctly. So if we plot the domain of this function, then what do we have? Suppose this is the unit circle on the complex z plane. So this is the unit circle with radius 1. And in order for this formula work, we need z, a complex number, must be greater than 1/2, which means that we have 1/2, and g must be a complex number on this reason. By the way, is this boundary included or not? Not, because we need strict inequality. So anyway, z equals 0, that bothered us initially, is not included here, right? So we just need to say, okay, this signal, this dt signal, the causal geometric sequence, has dt Fourier dt, the z transform that can be written as this one or that one if this is satisfied. By the way, are they the same in this reason? Yes. Why? In this reason, z equals 0 is not included, which means that it is guaranteed that it is okay to multiply z, any z, in this reason to the numerator and denominator, or divide by z. We can divide numerator and denominator. In that case, this is perfectly equivalent to that one. Got it? So your z transform now can be written in at least 3 forms. The first form is just a kind of series form. It could have countably infinite term because this is the definition, right? So some people say that this is not Z transform, you must simplify, but I don't agree with that, okay? Because this is the definition. Of course, still, it's your responsibility to find out the reason of so-called convergence of this infinite series. In order to find the reason of convergence, anyway, you may need to use, in this case, the geometric series infinite sum form. So anyway, you need this one or equivalently that one. Anyway, I gave you two examples. One is very simple. The other is a little bit complicated. And the reason why I talk about this example is that when you define a Z transform, Z transform is a function of complex number Z, but your domain of this function may not be the entire complex plane. So you have to specify the domain of your Z transform. But the domain of Z transform is called the region of convergence, ROC, region of convergence. Not just the domain, because definition of Z transform involves countably infinite term. So it's related to the whether some complex number is excluded from the domain is related to whether this sum converges or not. Right? That's why the domain of the Z transform is called region of convergence, ROC. Okay, so let's see what is written in the handout. The textbook says that the Z transform is motivated by the limitation of Fourier transform. And let's see what is the limitation. So as you see that this is the definition of Fourier series, and this is, Fourier transform, and this is inverse transform, right? And the textbook says that, unfortunately, some signals is not guaranteed to have its Fourier transform, because here, after you take the absolute value of this one, it may not converge. So as I just reviewed, the signal may not be absolutely summable. So we cannot handle some of the important signals using Fourier transform. Well, I don't agree with that actually. Yeah. The reason why Z transform is so useful is that actually we design the system only the scope where Z transform is useful. Got it? We may design some system only when the Fourier transform is useful. That's possible. But people have found that that has some trouble. Then Z transform is more powerful. Actually, it's not. It also has some limitation. But as we will see here, we design digital system after modeling it as a discrete time system. We love to use Z transform because it immediately gives us how many delay components we need, how can we truncate the signal, blah, blah, blah. Anyway, so I don't agree with this argument. Of course, it's very important whether signal is absolutely summable or not, mathematically speaking, but I don't agree. And the textbook says that the Z transform is a special case of Fourier. Fourier transform is a special case of Z transform. Why? As you've seen, Z transform is defined as what? X of n times Z to the negative n. Now here, you evaluate only for e to the j omega. And you may not grasp the meaning of this one, but here, this is entire complex plane. In the context of Z transform, we call it Z plane. Now, Z could be, in the Z transform, Z could be any complex number in the region of convergence, right? However, as you see here, from here to there, if you restrict your Z to e to the j omega, then you only consider this unit circle on the Z plane, which is what? A part of the Z transform with very, very restricted subset of the domain. So in this sense, people say that, hey, Fourier transform is a special case or specialization of Z transform. That is half correct. But our textbook also says that, see this. Now, let's start from the Z transform. Since Z is a complex number in general, it has magnitude and angle, right? Let's call its magnitude R and angle omega. Now, let's plug in this into Z here. Then what happens? We have sigma and summon, which is the product of the signal, and Z to the negative n, where Z is now replaced by R times e to the j omega. Now, we use the property of the base and exponent. So we have R to the negative n and e to the negative j omega n. And using the associativity, we put this first term together. Now, what is this one? This is nothing but the dt Fourier transform of the signal y, where y is the product of x of n times r to the negative n. By the way, what is this r to the negative n? This is a discrete time signal that spans from negative infinity to positive infinity with common ratio r. So two signals multiplied and then Fourier transformed. In this way, you may understand Z transform as a specialization of discrete time Fourier transform. So just claiming that the reason why we love Z transform is a generalization of DT Fourier transform is half correct and half incorrect. Because in other point of view, Z transform is a specialization of the discrete time Fourier transform. Got it? The reason why, in my point of view, the reason why Z transform is so powerful is that we are going to design DT system by using delay components and adders and multipliers. That's my point of view. Anyway, so here goes the definition kind of Z plane. And what is Z plane? It's just the complex plane, but since we use the variable Z, we call the plane, the complex plane, the Z plane. Got it? So you may just say this is complex plane. So this, right, the horizontal axis means real part of the complex number, and vertical axis means the imaginary part of the complex number. And about the reason of
Dr. Joe, it is
about the reason of convergence, I already told you when we introduced the definition of Z transform. Because Z transform is defined as an infinite sum of the terms. That sum could converge or not converge depending on the value of the complex number Z given your discrete time signal. So this is kind of obvious. And before I finish, let me just remind you your high school friend, 1 over x. Suppose you have two functions, f and g, that are both 1 over x. However, the f function has domain x positive and g function has domain x negative. Now, are they the same function? So f of x and g of x are the same functions? Definitely not. Why? You may plot and they are different, but see that this rule, this algebraic rule may be the same, but functions domain is different. If functions domains are different, they are not the same functions. Because a function, when it is defined, is always, first you say something like this. F, the function f, is from some domain to some possible range, right? If this is different, they are different functions. Same happens in the Z transform. And you have to remember this because this part troubled me until I studied the digital signal processing in graduate school. So be careful. Okay, so let me stop here. I hope you had good job in your first quiz and see you next week.